So today we're going to go over section 8.4, which is the vertex form of a parabola. And other background information, up until this section in 8.1 to 8.3, as well as 8.5, we've seen quadratic functions written two different ways. One of them has been standard form, in which case we can write the function f of x as ax squared plus bx plus c. And the other one we've seen was intercept, which we can also call factored form. And we saw those where it was essentially like trinomials, but they were already factored for us. So something like, and I'm just using m and n as any random numbers. So section 8.4 is just another form. So it's the third form that we know. There's a specific way we can use this form to make a graph. Just like when we look at intercept form, we know that we would use the intercepts to find the vertex, so on and so forth. So the vertex form of a parabola, first of all, can be written as f of x is equal to a, and then in parentheses, x minus h squared plus k. Now, just like with other forms like standard form, we did talk about how the letters a and c were responsible for some changes to the graph. We will have to do the same thing here. We want to know what each letter does. So a few things with vertex form. I'm going to bring up a graph of that. So what I have prepared over here is just the general a times x minus h squared plus k. So the first thing we want to do is identify, if I change the value of a, what is that going to do to my graph? So on the right side of the screen here, I'm going to hit play on a. And we can see we already know what a does. A is the same as before, meaning it's either going to flip the graph if a is negative. And then as we said before, if the absolute value of that number is bigger than 1, that is going to be our vertical stretch. And then if the absolute value of that number is less than 1, that was our vertical shrink. So a is the same thing as it was in standard form. It's the same thing that it is in intercept or factored form. That's why we've used the same letter of a. So I'm going to set a back to 1 so we don't have any stretch or shrink. Now for the h value, I'm going to hit play on the graph. We're going to see what h does. It should be fairly visual. I can clearly see that the value of h is moving my graph left and right. So we're going to call that a horizontal shift. Now we can be more specific. Like if I pause it here, it's clearly moved to the right. So if h was 3.8, it'd say x minus 3.8. So if it's x minus a number, it is going to move the graph right that number of units. And then if I get it to move left, well, I have to say something like this. I'm subtracting a negative. So when I see x plus a number in parentheses, that is going to move the graph left that number of units. The k value is our last thing. And again, we can see what the k value does. I'm going to set h back to 0. I'm going to hit play on k. We can see it's just moving that graph up or down. So we already know this as a vertical shift. And it does work out like we want it to. If it's adding k, then that'll go up k units. If it's a minus k, it goes down k units. This one is called k. We did talk about c as moving the graph up or down, but that's the y-intercept. And over here, k is not the y-intercept, which is why we call it something different. So the first thing we need to realize is that, as we said, we need to be able to understand what each of those letters does. So we need to memorize that. Now the reason why it's called vertex form is we can use the shifts to find the vertex. In other words, in vertex form, the vertex is at the point h, comma k. Now with that, it must be written in that form, x minus h squared plus k. If it's not as a minus, it doesn't work that way, but we'll see with the specific examples that when I move left or right, we're just moving the vertex. So that brings us to our first example. So intercept form of a parabola was called intercept form because we could find the x-intercepts of the equation. Like for example, if this was given in intercept form, the x plus 1 could have been a reason we got to 0, or the x minus 5 could have been the reason we got to 0, in which case I am able to find my x-intercepts. So vertex form is called vertex form because when I just look at the equation, I should be able to identify the vertex of the parabola just from the equation. So for example, if I start with something like x minus 3 squared plus 6. From what we just learned, the number inside is a minus. So on our notes, if there's a minus, it's going to move right that many units. So this moved right 3 units. And then since the number at the end is a plus 6, this moves it up 6 units. And remember, when we talk about transformations, we're describing it from the parent. So the parent's vertex was at 0, 0. If I move right 3, that would bring me to the point 3, 0. And then I need to move up 6, so that would bring me to the point 3, 6. So that's where the vertex is. If we see another example, something like y equals negative 5/4, x minus, or let's do x plus 2 squared minus 6. Well, if I wanted to find the vertex, this here has nothing to do with the location of the vertex. Because there's a negative, I know it's flipped over. And because the fraction, negative 5/4, absolute value is bigger than 1, that is going to be a vertical stretch. But that doesn't move the vertex. The only thing that's going to move the vertex are the values of h and k. So here, since I see a plus 2, according to our notes, a plus means we're going to move left, actually. So this would move left 2 units. The minus 6 at the end would tell us if it's minus, we're going to go down that number. So here, this is going to force us to move down 6 units. So if I wanted to find the vertex, we always know that the parent vertex is at 0, 0. So if I do my transformations, if I move 2 to the left, that would bring me to the point negative 2, 0. And then again, if I moved down 6, that would bring me to the point negative 2, negative 6. So this is where the vertex is. We've described, if we're looking at the directions, we want to describe the graphs. We've described that it's going to move left, it's going to move down, it would be flipped over, and it'd be vertically stretched. We could ask you to go backwards, right? If you want to think about writing an equation with a certain vertex, what we can see here is it's no longer at 0, 0. This vertex moved right 2 units and then up 3. If I started at 0, 0, I moved right 2 and up 3. So in my equation, if I want to move to the right a number, we know that moving to the right is actually subtracting that number. So if I want to move to the right 2, I would subtract 2, and then I have to square it. And up 3, if I want to move up, that is a positive number. So x minus 2 squared plus 3. Now again, with this one, if we compared it to the parent, which was at 0, 0, this one moved left 2 units and then down 3 units. So following the same idea, if it's going to be quadratic, we start with f of x. And since we want to have the vertex, we're going to use a vertex form. Now, if I want to move left 2 units, going back to our notes, moving left is actually adding that number. So I'd want to take x and add 2. And again, if I want to move down, that's the number at the end, and a negative number would move it down. So we have a minus 3. Moving on to number 3, a parabola that has been flipped over. When something is flipped over, that's the a value. The vertex is going to describe our h and our k. So we know we have a quadratic function. Now, if it's been flipped over, there needs to be a negative, right? Now, if the vertex was at positive 1, that means it moved right 1 on the x-axis. So in our parentheses, we should actually subtract 1. Then if the k value was a positive 1, that means it went up 1, and we know that k values follow their direction. Number 4, a parabola that's vertically shrunk. So this is an a value, and if it's shrunk, we know that a value's absolute value needs to be less than 1. So there was no movement left or right if the x value is at 0. But if the y value is at 5, we can see that the vertex compared to the parent moved up 5. So we can start with f of x. I need to choose any number that would shrink it, so I'm just going to choose 1/3. I don't want it to move left or right, so I'm just going to subtract 0. And if I want it to move up 5, I'd put a +5 at the end. So just working with the equation, you need to know what every letter does, and knowing that h and k will help you find the vertex. Now, the second part about the notes today is about graphing quadratic functions given in vertex form. I've already copied a list of steps that the textbook offers for us, and we are going to follow that list of steps on the 2 examples that we see down here. We're going to start with the first example, number 1 on the left-hand side here. Just reading the list of steps, it wants us to graph the axis of symmetry, find the vertex, plot some more points, use reflection, and then draw a parabola. The first thing I would say is, according to your textbook, it is okay to flip those around. I might actually plot the vertex first. So if we look at the first equation here, let's predict what it should look like. So there's an a value, so the negative is going to cause it to flip over. And then because the absolute value of -2 is bigger than 1, this is going to cause a vertical stretch. So it should be a little skinny, is how we actually see it on the graph. Now, we'll go over to the h value, and since it's a minus, again, we know that minus actually moves it to the right. So this is going to move it to the right 1 unit. And then our k value is a +6. And we know that if it's up, it's a positive. So +6 means we go up 6 units. So if I needed to plot the vertex, we could think about the parent vertex. Starts at 0, 0. But if I follow the idea of moving right 1 and then up 6, we could do that in parts. Well, if I move right 1, my x value would change to +1. And then if I moved up 6, my y value would change to +6. So my vertex is at the point 1, 6. Now in a graph like this, we are just going to make our own coordinate plane. And we're going to graph the point 1, 6 just to be right here. And you can put that wherever you want. So this is the point 1, 6. Once we have that vertex, then I think it's a little bit easier to find the axis of symmetry because we know it goes through the vertex, and the x value of the vertex is the equation of the axis of symmetry. Now, we need to find 2 more points. I highly suggest the y-intercept be one of those. Or we can choose any x value we want. Because if we have an x value, let's say 0, if I want to plug that into the equation, I just follow the equation to help me get its output. So 0 minus 1 is -1. I'd square that. So -1 squared is 1. 1 times -2 is -2. Adding 6 gives me 4. So if I plugged in 0, I get the output of 4. So the x value of 0 should have the y value of 4. Now this starts to look good, right? If I think my graph is flipped over, then my vertex should be the tallest point. So I need one other point to plug in. It doesn't matter where I do it. I'm just going to choose a random x value. I'm going to choose -1. So if I plugged in -1 and do a little simplification, so inside parentheses, that turns into -2. So -2 squared is 4. 4 times -2 is -8, and then I'd add 6. So it gives me -2. So at -1, I should be down here at -2. So once we have 2 points, we then are supposed to use reflection, or in other words, the partner points, to find more. So we're going to go do that. So this x value here was 0. So over to the middle was a distance of 1 on the x-axis. So I'd go 1 more, which would bring my x value to 2, and we know that partner points have the same y value. We could find this partner point down here. If the x started at -1 and I got halfway at x equals 1, that's a distance of 2. So I'd travel a distance of 2 again, which would bring my x value to 3, and the y values are the same. The last step, it says draw a parabola through the points. Make sure we plotted enough points to make that nice parabolic shape. And if I connected the dots, it's not perfect, but it does make a U-shaped graph. So I'd be done with that example there. Now, the one thing I'm going to go back and look is the vertex was supposed to be 1 to the right and up 6. So I do see that there. My graph's not perfect, but it's pretty good. It is flipped over. Just as a heads up, this is going to be hard to see at times when you talk about stretches and shrinks. So if we bring back the actual parent function in the graph, if we set a to -2, and then the h value, so x minus 1, so here, so it should move right 1, and then the up 6, so a positive 6. Now in this version, it's a little bit easier to see that the red graph actually is skinnier than the parent graph, which is in the dotted black. But when you draw it over here, it's okay if it's hard to see. So what you could do just to indicate to your teachers, say like, this should look skinny compared to the parent. And it's okay to indicate that as well. So let's go ahead and do one more example here. Now on this one, we needed to, f of x is 1/2 of x plus 2 squared minus 4. And you'll notice that I, in my head, already changed 0.5 to 1/2, just so we could see that that number is less than 1. So when I see that 1/2 here, that's going to cause a vertical shrink. Doesn't move the vertex, but it helps me describe what my graph should look like. And there is no flip or anything, so it should look like it's up like a cup. When I see a +2, that's actually going to move my vertex to the left 2 units. And as we've seen before, the -4 at the end moves it down 4. So again, I'm just going to make a coordinate plane so I can make my own graph here. So if the vertex started at 0, 0, because that's where the parent is, I follow the motions or the movement to find the new vertex. So if I went left 2 units, my x value would be -2. So again, I'm not starting at the parent vertex, that's 0, 0. I'm following the movements. So I went left 2 and then down 4. That point right here is -2, -4. So we plot the vertex first. Or if you really wanted to, you could do the axis of symmetry first. Doesn't matter if steps 1 and 2. We know the axis of symmetry is at the value x equals -2. I'm going to erase my parent vertex. I'm just going to fill that back in on black so we don't confuse it for a point on our graph. Now we just need to find 2 other points on our graph. So like I said, plugging in x equals 0 is usually pretty easy. So down here, if I plugged in 0, I'd be taking 1/2 of 0 plus 2 squared, and then I would subtract 4 at the end. So that's 1/2 2 squared minus 4. So half of 4 minus 4, which is 2 minus 4, which brings me to -2. So the vertex had the the y-intercept had the x value of 0 and the y value of -2. I just need one more point, so I'm just going to choose the x value of 1. So if I took my function and plugged in 1, I'd be taking 1 plus 2, and squaring it, and then minusing 4. I'm actually going to change my mind. I don't want to use 1. I'm going to change that to 2 right away, just because my denominator is a 2, so I want to divide by a number that's divisible by 2. So 1/2 of 4 squared minus 4. So 4 squared is 16, so half of 16 is 8, and if I subtracted 4, I would get 4 back. So if I plugged in 2, I get the output of 4. I'm just going to go ahead and plot that somewhere over here. That's 2, 4. So then according to the list of steps, once I plot those 2 points, I just need to use symmetry to get their other side. So the distance to the axis of symmetry was 2. So if I go 2 more, that would bring me to the point -4, and then the y value is still the same at -2. So that's one of our symmetrical points. If I find this partner point, it was a distance of 4 to the middle. So getting to the other side, I would travel another distance of 4, which would bring me to -6 on the x-axis, and the y-axis stays the same. And then I do note that if I were to connect these dots, I would make a nice smooth parabola. And again, it's harder to see that this is a vertical shrink because of our own scale, so we can go ahead and say should look skinny, or indicate to our teacher that this actually would look vertically shrunk. It's just hard to see if we don't have our parent there. So if we go back and compare it to the parent, if we set our a value to 0.5, and then we set our h value so it's a +2, again, minus and negative would be a plus, and then our k value is supposed to be -4, which I guess I have to change. So if I set that to -4, we can see that the red graph is actually wider, in other words, vertically shrunk compared to the parent graph.